Всем привет, это моя первый тайм в Минске. У меня очень плохой русский, поэтому я буду докладывать на английском. Today I'll be talking about the research project that I originally started as my master thesis at Ukrainian Catholic University, and now I'm working on it further. So here's the quick agenda. Let's start. You all probably know about the problem of overfitting. It's relevant for the deep neural networks, and there are many ways how to reduce overfitting. I will focus my research on perhaps the most widely used one called data augmentation. Data augmentation can be divided by two categories. Traditional data augmentation, that is using label preserving transformations such as cropping, blurring, horizontal flips, etc. And generative data augmentation by using mainly generative adversarial networks. In my research, I'll focus only on traditional data augmentations. Data augmentation is really great. It's easy to use, efficient to implement, but it also has some drawbacks. For example, it can produce irrelevant data. Imagine that we have a data set with digits, and for example, we flip the 9, so the result is no longer a valid digit. And if with digits, it's easy for us to distinguish which data augmentations make sense and which does not. If we, for example, take MRI images of the brain, it's obviously that without the medical education, it's really hard to tell which data augmentation will be useful for these types of data. And that leads us to the problem station. In our research, we are aiming to automate the process of choosing relevant data augmentation, which can be safely used during the training of the original task. Or more formally, we will have a data set D and a set of all available augmentations A, and the task is to choose the subset of safe augmentations. We propose to solve this problem using a 4-steps pipeline. The first step is to solve the following multi-label classification problem. So each image is augmented with a random subset of data augmentation, and model tries to predict which augmentations were applied. In order to take into the account the image classification accuracy or image segmentation accuracy, we train this step 1 in joint learning setup. So our total loss is defined as augmentation classification loss plus the loss of the original task. That is image classification or image segmentation. Next step, after our model is being trained, we evaluate that on the clean test set and collect false positives for each data augmentation. Step 3 is the same test set, but now it's augmented in the same way as during training, and we collect the per label accuracy. So for each data augmentation, we collect its accuracy. And the final step is to choose the subset of safe augmentation. Augmentation is considered safe if it has low false positive rate on clean set and low per label accuracy on augmented test set. So what is the overall intuition of our method is to choose data augmentation which lead to images that are similar to those we already have in the training data. Here is a quick example of step 2 and step 3. You can see on y-axis its image classification accuracy. Red line denotes the image classification accuracy without any augmentation. Here you can see step 2, it's false positives from the clean test set. Here is augmentation classification accuracy, step 3. And let me show you which augmentation we consider as safe. For example, horizontal flip, number 1. It has 0 false positives and also really low augmentation classification accuracy. And you can see how it adds to the overall image classification accuracy. On the other hand, if you take blur, number 13, it also has 0 false positives, but it's really high augmentation classification accuracy. And you can see that the accuracy of the model trained with blur is even lower than trained without any augmentations. How we propose to use our safe augmentation? There are 2 ways. First is for model fine-tuning. We experiment with pre-training on all augmentations and fine-tuning on safe augmentations, and also along with other augmentation techniques. Here you can see the example of from CFAR 100 and street view house number data sets. We're using some subsets of size 3, each augmentation with probability 0.5. You can see that the images look pretty similar. We can easily recognize objects on them, but it still adds some variability to our data set. So experimental part, we evaluate our approach on several most popular image classification data sets, and on cityscapes, we evaluate the semantic segmentation task. Here you can see a list of all augmentations A that we used. It's 15 most popular augmentations. We use them with the default magnitude. You can see the results of found safe augmentation for each image classification data set. We can see that for CFARs and TinyImageNet, they look pretty the same, which makes sense because the images there also look similarly. One thing to mention that using this approach, we can only evaluate one data augmentation at a time. So we cannot take into the account the impact of one augmentation on another when applying together. That's it. So here we have 3 different crops, and if they apply it separately, it is for sure safe augmentation. But if they apply it together, it may no longer be safe. We also experiment with different subset sizes. Here you can see results from the CFAR data set, and we decided to use the subset size 3 because it yields the best image classification accuracy both for all augmentations and for safe augmentation. Here is the results from all the data set from image classification task. We tried training without augmentation, using only our safe augmentation, using subsets of all augmentations, and also we try pre-training on all augmentation and fine-tuning on all, pre-training on all and fine-tuning on safe, and pre-training on all and fine-tuning on safe augmentation V2. What is safe augmentation V2? It is defined manually by removing two of the 3 crops. As I said, because we cannot take into account impact of different augmentation on each other. You can see that pre-training on all augmentations and fine-tuning on safe leads to the best accuracy on all data sets, comparing to different tries with different subsets of augmentations. When we speak about similar methods, I need to speak about auto-augment. It's the current state of the art of choosing data augmentations. The idea is they use reinforcement learning to find pairs of data augmentation functions along with all the hyperparameters that directly maximize the image classification accuracy. As you can imagine, the search space is huge, and it for sure takes a lot of computational power, but works with superior quality. And the previous state of the art for the image classification tasks is cutout. Really simple idea, you just cut out random squares of your image. We also compare our approach with these 2 mentioned previously. Here we trained without augmentation, only with best policy found by AutoAugment, with baseline augmentations, cut out our augmentations in AutoAugment setup. So our augmentation plus baseline plus cutout and AutoAugment. For sure, AutoAugment leads to the best quality, the best accuracy, but our method on CFR 100 and street view house number works better than the cutout. On CFR 10, it works slightly worse, but still it is better than the baseline augmentations on all the data sets. That semantic segmentation task, we also tried on semantic segmentation using FPN with DenseNet backbone. Here you can see the found safe augmentations for this data set. It is the same. All fine-tuning was performed on a model pre-trained on all augmentation. And you can see that fine-tuning on safe augmentation also leads to the best accuracy. It's intersection over union on validation. In conclusion, our method is really simple. It works with different tasks. We show with image classification and image segmentation. It is computationally efficient. It does not require domain expert knowledge. And still, it leads to good accuracy of the original task. What about disadvantages? It's still not a fully automated approach. We have these manual steps where we select safe augmentation. And it highly depended on initial set of all augmentations. It depends on all the hyperparameters that were used in initial set. And the final one, as I said, we can only evaluate each transformation independently of other. That's it. Thank you, and I will be happy to take questions.
Ну а теперь опять минутка вопросов.
Okay, first of all, thank you very much for your nice presentation. And my question is about whether we can use efficiently images generated by GANs as for augmentation purposes, because they are now very flexible. So classical DC GAN is just produced good texture, and new GANs, progressive GANs produce good shape, etc. So okay, what do you think, whether we can use efficiently artificial images generated by GANs as augmentation way of augmentation?
Okay, yeah, thank you for the question. So the question was if we can use GANs for data augmentation efficiently, yes? I think that currently GANs are still developing, and it's hard to train them properly. So there are a lot of pitfalls. I mean, it's really hard to train them properly to have good data augmentation. When we speak about our approach, it's really simple. You have your model for your original task, image classification, and you just add some additional steps to train it using call augmentation, and then you can find easily a safe augmentation. So our approach is, I think, convenient for anybody to implement. But when we're speaking about GANs, I think that it's not still production ready.
Do you know any kind of experimental works on that? Because, for instance, we're able to generate now images nobody can distinguish from real ones.
Yeah.
So why not to use them? They fulfill all the requirements you listed at the beginning.
I know cycle GANs, I have examples somewhere. Okay, here they can generate scenes in completely different season, but it's still research. Our approach, I think, is more practical. It can work with any data, and I don't know.
Thank you very much.
Thanks.
У нас есть время еще буквально на один вопрос. Не стесняйтесь задавать вопрос на русском. Докладчик, в принципе, все понимает.
Я понимаю, все, да.
Да. Просто доклад удобнее читать было на английском. Вот. Есть желающие? Или начну я?
Okay, I have a microphone, so let me ask a question. So thank you for your talk first, but I kind of didn't get the main motivation. So usually augmentation is used to supply more information to the network. However, when you make it safe, you kind of supply network with the examples that already work good in this network. Do you have any metric which compares like the gain in accuracy with some metric of safeness of the augmentation? Like there should be some graph like that. Because if you only supply augmentations which are very easy for the network, it doesn't learn anything from it.
Yeah, that's idea of our research is to find, as you said, augmentation that leads to the data similar to the data to those we have already in data set, but still different somehow. And as I said, we propose to use them, not only use our safe augmentation and that's it. We propose to use them along with other augmentation techniques. Or another approach is, as we tried, retrain on all augmentation and then fine-tune on safe. Because if you're using only safe augmentation, you will not gain much accuracy. You can see here. If you use only safe augmentation, it's almost the same as not using augmentations at all. But if you use them with other augmentation techniques, or if you're fine-tuning the already pre-trained model, it still adds some accuracy.
Ну, давайте поаплодируем докладчику, раз вопросов больше нету.
Спасибо.
Ну и не боимся применять все это на практике. Это действительно очень крутая, полезная работа.